Alright, just like you've already learned with solving exponential equations, you can also solve logarithmic equations. Logarithmic equations are just equations that involve logarithms. Alright, and when we solved exponential equations, we saw that there was a property of equality for exponential equations, and that one was something along these lines, like if you had 2 to the power of x, and that equaled the same base number to some other exponent, that you could say simply that x must equal 2. Logarithm equations have the exact same property, and it's displayed right here. It says if you have log base 2 of x, and you are told that that equals log base 2 of 7, then, by common sense and the property of equality for logarithm equations, you can say that x equals 7. Here's an example of the property of inequality. This one is a logarithmic equation. It says log base 5 of 4x minus 7 equals log base 5 of x plus 5. Because your base numbers are the same for the logs, you are allowed to assume that the arguments 4x minus 7 must equal x plus 5. Remember, your job is to solve, and that means we're solving for x. So at this point you would just clean up your equation and then figure out that x equals 4. Alright, but as with exponential equations, it wasn't always that easy to solve them. And so we need to look at what happens when we have a situation like this. You can see in this problem that you're supposed to solve log base 4 of 5x minus 1, and that equals 3. Well, I don't have two logs, one on each side with the same base, so we need to look at a second method for solving logarithmic equations. That second method is called exponentiation, or exponentiating logs. And how you need to think about this is, I have a sentence here that I need to somehow free my x from the argument of the log. And so what we end up doing is taking this entire sentence and shoving it kind of up into the exponent of a new equivalent sentence. And we're going to do that using some of the cancellation properties. So let's look at this closer. I have log base 4. What base number could I put on that side of the equation to make log base 4 cancel? This is what you end up doing. You put 4 down as your base number, and then you take this side, the left side, and put it up into the exponent. You're kind of shoving this whole thing up into the exponent. And hopefully now you can see why, because base 4 to the log base 4 power is going to cancel. And of course with algebra, whatever you do to one side you must do to the other. So I'm going to put a base number 4 there and slide that 3 that was on the right side up into the exponent. And this is what your new equivalent equation looks like. And because of your cancellation property, you can cross those out. And then you know from that property that you are left with 5x minus 1, and that's going to equal 4 to the third power, which is just 64. And now you can just go about solving it. And so you would add 1 to both sides, so you get 5x equals 65, and then divide by 5 to get 13. That one is a little harder to sometimes understand, so we're going to skip right to our guided practice problems, but as always, we need to eventually look at extraneous solutions occurring. And again, we can just look for those by checking our answers by substituting them into the original equation. But let's jump to the guided practice. I want to work along with you on these, but if you feel like you know it already, go ahead and pause the video. I'm just going to keep talking though and walk our way through these. So looking at problem number 7, you're going to use your equality property on this one. It's kind of that method 1 for solving logs. Because I have log base e on both sides, you can assume then that 7x, the argument on the left side, must equal the argument on the right side. And go ahead and solve that by subtracting 2x from both sides and then adding 4 to get 15, and you see that x equals 3. And I talked about solving exponential equations, and so you can check these from now on. It says to check extraneous solutions by substituting this 3 back into the left side and the right side. And get your calculator out, and we'll do that. And when I check on my calculator, I get the left and right side both equaling 2.8 something. And so you can say, in fact, that this is truly 2.83, I guess, equals 2.83. So you can say yes, in fact, that is a solution that works. All right, let's look at number 8. This one is our second method because I have log base 2 of x minus 6 equaling 5. I cannot use method 1, that equality property. I need to exponentiate this entire sentence, meaning shove it into the exponent and attach it to a new base number that would cancel log base 2. So what number would cancel log base 2? Well, that would be a base number of 2. Now sometimes, let me erase that, if you don't want to be rewriting these all the time, people kind of cheat and they just write a big 2 right here and a big 2 right there as your base numbers, and then if you look at this you can see that it's all new. I've taken this and now it looks like it's the exponent. So I have 2 to the power of log base 2 of x minus 6 and 2 to the power of 5. And so, using the cancellation properties, you know that this cancels, and then you are left with x minus 6 on the left and 2 to the power of 5, which is 32 on the right. Add 6 to both sides, and you're going to get that x equals 38. And let's check that with our calculator. You check it back into the original equation. We're going to have to use our change of base formula. So I'm going to have x minus 6, so you get 38 minus 6, which is just 32, and it's log base 2 of 32. And so to change that base, we're going to say log 32, and that'll be our common log, over log 2, and then we will see if that indeed is 5. So log 2 divided by, I'm sorry, log 32, I'm doing it right along with you right now, divided by log 2 is indeed 5. So we have checked that. That is not an extraneous solution. X really is 38. Alright, this next one, number 9, is a great problem in that you can see you have some logarithmic properties at play here. I have an addition sign here, and I can't use any of my methods when I have an addition sign there. So we're going to use our log properties, and you should know that when you're adding logs, it is equivalent to saying that you are multiplying the arguments together. So inside this new argument, I have 5x times x minus 1. And that is just, again, a log property, the product property actually of logs. And so now I have my log base 10 isolated on this side of the equation, and so right now I'm going to exponentiate it. So you need to understand that this is log base 10 right here, and so my new base number is going to become 10. I'll put 10 right here so I don't have to write it twice, but I'm rewriting this as a whole new equivalent equation that's now exponential. So now I can cancel 10 to the power of log base 10, and then on my left side I end up with 5x squared minus 5x equals 10 to the power of 2, which is just 100. And now we can go about solving this. It is quadratic, so I'm going to get 5x squared minus 5x minus 100 equals 0. And of course, we start off by dividing out a common factor, and so 5 will be divided out, and I'm left with x squared minus x minus 20 equals 0. And then factoring that, you can ignore the 5 now because it's just going to go away. You are left, you could do x minus 5 and x plus 4 equals 0, telling you that x equals 5 or x must equal negative 4. So I'm going to pause the video because I need to check for extraneous solutions, and so I will put each one of these in, and we'll decide if they're both solutions or not. Alright, and here was my result. That 5 did indeed produce a 2 when put into the original equation, but -4 you ended up with imaginary numbers, and so this is not a solution, it is extraneous. This also over here, when you're just plugging in to check for extraneous, you could just plug it right into your calculator, so you don't have to hesitate about that. Alright, let's look at number 10. Again, you can pause it if you think you know how to do it, but I'm going to walk us through this. So here I have log base 4 and another log base 4, but I have this addition inside here, and I kind of want to isolate my logs or bring them together using the product property. And so this one you will end up with log base 4 of, and then we'll just say that we have x plus 12, that one argument times x, and that equals 3. And now you're at the point where you can undo the log by taking the exponent or making it an exponent. And so the base number that I would use for this is a large 4 for the base number, and now that black writing has become the exponent. Again, it's called exponentiation. So because of the cancellation property, these go away, and then I'm just going to multiply out that x times everything inside there, and so you're going to end up with x squared plus 12x, and then on the right side you have 4 to the third power, which is 64. And continuing on solving the quadratic, you have x squared plus 12x minus 64, and that equals 0. So what two numbers when multiplied give you 64, but when added give you 12, and that is 16 and 4. No lie, I paused the video to make sure I was right. But, so we're going to have a positive 16 and a negative 4, and that equals 0. And so our solutions could be negative 16 or a positive 4. So let's check those, and we'll see if any of them are extraneous. And I actually had both of them working on that one, so that's kind of cool. Alright, good luck with logarithms. Again, you can review that video anytime you need to. Here's a word problem, in case you want to see it in action. Feel free. This one says the apparent magnitude of a star is a measure of the brightness of the star as it appears to observers on Earth. The apparent magnitude m of the dimmest star can be seen with a telescope, given by the function that they show you. So thank goodness we don't have to write that. But it says d is the diameter in millimeters of the telescope's objective lens. If a telescope can reveal stars with a magnitude of 12, what is the diameter of its objective lens? Alright, so in the problem we're given the magnitude is actually 12, and so we'll use that equation and substitute 12 in for m, and we have 5 log base d. D happens to be what we're looking for. As with most equations, when you solve them, you're going to need to isolate this log part, the log d, and so we're going to undo everything else. So I'm going to subtract 2 first from both sides. You end up with 10 equals 5 log d. Divide both sides by 5, and you'll end up with 2 log its base 10 of d. And now we want to solve for d, but it is trapped in the log, and so this is a method where you need to exponentiate or make this thing the exponent of a base number that will eliminate the log. And so since it's log base 10, my new base number will be 10. So again, you need to look at this and think of this as a new exponential equation. Here, my 10 and log base 10 in the exponent cancel each other, and so you are left with the answer, which is 100 equals d, and so the diameter of the objective lens is 100 millimeters.